Welcome to this lecture on transition metal organometallic chemistry from principles to applications. We have been discussing a very important topic of σ-alkyl transition metal complexes, which is about CH activation. Now, in the last lecture we had seen that CH activation originates with CH-M agostic interactions. These CH-N agostic interactions leads to CH activation, where splitting of CH bond occurs, whereas in agostic interaction only weakening of CH bond occurs. Finally, proper chemical manipulation at the stage of CH bond activation will lead to CH bond functionalization, where CFG Fg equals functional group bond is formed. Now, this has lot of utility in chemical industry because it creates value added chemicals. In our last class, we have seen a very nice example of this whole pathway from agostic interaction to CH activation to CH functionalization as demonstrated by Shilov, who using this following sequence of strategy was able to convert methane to methanol as well as methane to methyl chloride. In the previous lecture, we have also seen that between these two sequences of CH activation as well as CH functionalization, CH activation was performed in a catalytic fashion, whereas CH functionalization was done in a stoichiometric fashion. In stoichiometric fashion. Now, with that we are going to take up some more examples with regard to these various CH activation and subsequently leading to CH functionalization. Now, before we do that, let us focus on the initial stages of the reaction, which is about agostic interaction, which sort of can be defined as alkane metal complex, or similar to this interaction there can be sigma alkyl transition metal complex, which would also initiate CH activation reaction. Now, as for the formation of sigma alkyl complexes leading to CH activation, the prior requirements are that the transition metal complex has to be coordinatively unsaturated, so that there is room for addition of the alkane to the transition metal. It also has to be electronically unsaturated, so that the metal complex is not inert by reaching the inert gas configuration in its valence shell. And the last condition is that the transition metal has to be electron rich. This is an important criteria for stabilizing transition metal sigma alkyl complexes. Let me illustrate this with an example. For example, this Cp star iridium hydride complex this is in iridium plus 3 oxidation state, and it has 18 valence electron. So, this is both coordinatively saturated as well as electronically saturated, and hence would not be forming a alkane complex. So, the way to get about it is reacting this 18 electron electronically and coordinatively saturated complex with an alkane under light results in elimination of hydrogen, which will make the compound coordinatively as well as electronically unsaturated, and to this alkane would bind, and alkane while binding would undergo oxidative addition reaction resulting in the corresponding iridium 3 complex as shown below. So, iridium in this complex, a methyl iridium has undergone CH activation over here and has produced this iridium hydride complex, which also is a iridium 3 complex having 18 valence electron. What is important in this reaction is that for this reaction to proceed, elimination of hydrogen is critical, because it will make the iridium complex both coordinatively and electronically unsaturated, and after that the oxidative addition of CH of the substrate would occur, leading to the corresponding iridium hydride complex. The same strategy is applied for another iridium complex, this cyclopentadienyl iridium dicarbonyl. This also is a 18 valence electron compound, hence electronically inert. It has an oxidation state of iridium +1. This in presence of light under high pressure of methane 10 bar in C6F12 medium eliminates 1 carbon monoxide to give the corresponding 16 electron complex, which is electronically unsaturated, and to that oxidative addition of methane occur, giving rise to this iridium complex. Here iridium is in +3 oxidation state, and it also has 18 valence electron. So, comparing these two examples, what one sees that electronically as well as coordinatively saturated compounds in presence of light becomes both coordinatively and electronically unsaturated by release of any of its existing ligands, after which it undergoes CH activation of the alkane, producing metal hydride alkyl complex as shown over here. Here also we see that the CH of this carbon and hydrogen undergo oxidative addition, similar to what was shown over here. Another example is seen in a platinum complex of the type shown over here. This is a square planar platinum complex having oxidation state of +2, and it has 16 valence electron. at 45 degrees centigrade, it eliminates neopentane and produces a platinum 2 species, which then activates the CH bond of cyclopropane substrate, giving rise to corresponding platinum hydride complex of the type shown here. Here too the oxidation state of platinum is +2, and in the final product platinum has 16 valence electron. The oxidative addition of the CH bond between the cyclopropyl carbon and this hydrogen occur to give the platinum hydride complex similar to the iridium hydride complex as well as this iridium hydride complex. So, comparing this example, what becomes clear is that sigma transition metal alkyl complexes containing activated CH bonds may be obtained even for transition metal complexes that are coordinatively as well as electronically saturated, but which undergoes a loss of ligand either by heat or by light, leading to an intermediate which is coordinatively as well as electronically unsaturated, and which then subsequently undergoes CH activation by oxidative reaction with alkane. Now, if we look at all of these examples and look how this reaction proceeded, what becomes clear is that the first two criteria has been reached by loss of all these ligands that would ensure electronic and coordinative unsaturation occurring for these complexes. Now, as for the third criteria, electron richness is concerned, it becomes clear that all of these transition metal alkyl complex hydridoalkyl complexes that have shown CH activation occur for late transition electron rich late transition metal complexes. So, this is an interesting observation that apart from electronic and coordinating unsaturation, electron richness is required for making these alkane complexes of transition metal. As can be seen that most of the alkane complexes of transition metal are observed for late transition metal complexes which are inherently electron rich. When we look at more detail as to the interaction, molecular level interaction occurring in stabilizing these CH activation reactions, we would see in greater detail the reason for electron richness affecting this reaction significantly. Now, the first catalytic application of CH bond leading to bond activation leading to functionalization was demonstrated by Hartwig as late as in the year 2000. By Hartwig, John Hartwig, now this also is a seminal work in the sense that three important criteria were fulfilled. One is thermal, then thermal way of carrying out CH functionalization. Not only that, this functionalization has been achieved in a catalytic fashion, and that too in a regioselective fashion, where selectivity is a major challenge in CH functionalization reaction. Let me provide the example of this reaction. For this long chain alkane, this is an octane the terminal CH bond is functionalized, first activated and then functionalized with this catalyst rhodium eta 4 C6 Me6 requires high temperature of 150 degrees centigrades and boron reagents this and this or its monomer giving the corresponding boronic ester in very high yield, 80% yield. So, and in the process elimination of hydrogen is observed. So, this reaction has selectivity because only this terminal CH is replaced by the boronic ester done in a catalytic fashion and also requires high thermal conditions. So, gradually with understanding of how CH bond is activated, the subsequent utility of CH bond activation is manifested in CH bond functionalization through the conversion of alkane to various functionalized product, for example, this boronic ester. I must note that this boronic ester is a useful starting precursor for Suzuki-Miura cross coupling reaction. Bond forming reaction. So, one of the limitation of Suzuki had been that though this Suzuki cross coupling reaction is a very useful synthetic tool for making various cross coupling product, but the challenge had been that synthesis of these boronic esters were not easy and very challenging. So, here in that perspective, this reaction by Hartwig gives easy access to boronic ester with high regioselectivity in high yields of about 80% using the simple concept of CH functionalization activation followed by CH functionalization reaction. Now, one needs to sort of understand that how does CH activation and functionalization occur. So, at what point does this oxidation step occur? What are the electronic requirement at the metal center? These had been the key features that we have been trying to understand through this lecture. In this regard, in this particular lecture, we have looked at two such examples. One was the CH activation as well as functionalization using Shilov's work, where methane could be converted to methanol and methyl chloride. And second such example was the conversion of long chain alkane to alkane boronic ester using Hartwig's work, which achieved this conversion under regioselective catalytic and thermal conditions. So, gradually as the understanding of CH activation and CH functionalization are happening, a lot more applications of such strategy are being seen in place. And in this class, let me just summarize that apart from the requirement for formation of this kind of sigma alkane complexes, we have also looked at some of the examples where these sigma alkane complexes have been isolated. And in such cases, what came to the fore is that the metal has to be both electronically as well as sterically unsaturated, and also it has to be that the metal center is electron rich, and which can be ascertained by the fact that the most of the transition metal sigma alkyl complexes which have been isolated, they are for very electron rich red transition metal ones. Now, with this we are going to take a look at some very interesting topic proceeding CH activation and functionalization, particularly how does an alkane bind if after it has undergone a CH activation, how does it bind to the transition metal, what are its mode of interaction with the transition metal, how does that have affect the CH activation and sub CH functionalization pathways. All of these would be discussed in more detail in the lecture which is succeeding this one, and with that I thank you for being with me in this lecture and look forward to being with you in the next lecture discussing on various modes of binding of alkanes to the transition metal in the context of transition metal sigma alkyl complexes. Thank you.